Okay, so this is sample problem 16.18. Oxalic acid, which has the chemical formula H2C2O4, is a poisonous substance used mainly as a bleaching agent. Calculate the concentrations of all species present at equilibrium in a 0.10 molar solution at 25 degrees C. So this is an example of a polyprotic acid. Oxalic acid has two acidic hydrogens. The formula for oxalic acid is H2C2O4. It will react with water. It's a diprotic acid. As a weak acid, so we'll lose one of the H pluses. And form a hydronium. So here's what we're going to do. We're going to do an ice problem on this one. The initial concentration is 0.10 molar. Don't need to worry about liquids. These start as 0. Now let's look up the value of K. Because it's a diprotic acid, it's actually going to have more than one Ka. So we're going to call the first one Ka1, and the value of Ka1 for oxalic acid is 6.5 times 10 to the minus 2. Now, where did I get that? I got that from table 16.8. But because it's a diprotic acid, it also has a second Ka, so we'll call that Ka2, the second hydrogen. And its value will be different than the first. And so its value for the Ka2 is 6.1 times 10 to the minus 5. For diprotic or triprotic acids, the second H plus is a weaker acid than the first one. And if there's a third one, it's weaker than the second. Okay? So you will always see that Ka2 is smaller than Ka1, usually by a large amount. Not by a factor of 2 or 5, but by a factor of 1,000. Okay? So let's take a look at how we go about this. Clearly it has a Ka, so that means Q is less than K because Q is 0. So that means it's minus X, plus X, plus X, and so at equilibrium it's 0.10 minus X, X and X. So that means we're going to use the Ka1. Ka1 is equal to concentration of HC2O4 minus times the concentration of H3O plus divided by the concentration of H2, O4. And that is equal to 6.5 times 10 to the negative 2. And that would also be equal to x squared over 0.10 minus x. Right? Now, here is an example where you cannot make the assumption that 0.10 minus x is approximately equal to 0.10. And the reason is this is so big here. When this is negative 4, negative 5, even negative 3 sometimes, you can make that assumption. But when you get up to negative 2, it's just not a good assumption, which means we cannot simplify in this case. Okay? So that means we got to go about it the hard way. We got to use the quadratic formula. So let's set it up for our general formula, ax squared plus bx plus c equals 0, and that will allow us to figure out the equilibrium concentrations of everything, which is really what they're asking us to do. Okay? So let's take the denominator over here, multiply it by that number, and set that equal to x squared. So x squared would be 6.5 times 10 to the minus 3 minus 6.5 times 10 to the minus 2 x. All right? So now we can just move the two terms on the right over to the left. So I'm going to add 6.5 times 10 to the minus 2x because it's a minus here, so adding it. And then we're going to subtract 6.5 times 10 to the minus 3, and that'll give us 0. Okay. Now, we've got our a, b, and c. So x is minus b, so that's minus 6.5 times 10 to the minus 2, plus or minus b squared. 6.5 times 10 to the minus 2 squared. Sorry about that. Minus b plus or minus b squared, minus 4 times a, which is 1, times negative 6.5 times 10 to the minus 3, which is c. b squared minus 4ac, all over 2a. Oops. Okay, so now we have to figure out what this is. Now keep in mind, in the radical, it's a minus, right? We're subtracting 4 times 1 times negative 6.5 times 10 to the minus 3. Okay, so let me get some room here. And we'll go through that. 6.5 times 10 to the minus 2 squared. Minus 4ac, so plus 4 times 1 times 6.5 times 10 to the minus 3. And then we need to have the square root of that. So the square root is 0.173, or 0.174. Now, if you take a look at this, you've got negative 6.5 times 10 to the minus 2 plus 0.174 or minus 0.174. So if you use the minus, you'll get a negative value. And we don't want a negative value for x, because if you get a negative value for x, that means the reaction is actually going to the left. And we've already decided it's going to the right. So we're going to take the plus. So 6.5 times 10 to the minus 2 negative plus 0.174. Well, that's the same. So that's the same as taking the second number and subtracting the first one, and then dividing it by 2. Okay? If you're doing the x plus, the positive root. Okay? You can check that, but that's what essentially. So now, there we go. So now, 0.174, which we already have in the calculator, we're going to subtract from that 6.5 times 10 to the minus 2, and then divide it by 2. So minus 6.5 times 10 to the minus 2, and then divide it by 2. 0.054. It's actually 0.544. I'll leave an extra sig fig in there. So we figured out what x is, okay? So now, here's the significance of that. The concentration of H2, C2O4 is 0.1 minus that. Okay? So 0.1 minus 0.0544. .0456. So there's one of the answers. At equilibrium, H2C2O4 is that value right there. Okay? Now, here's the issue that comes up with HC2O4 minus, the products. The HC2O4 minus is an acid itself. which means that it's going to lose some H plus itself. So that means its final concentration is not going to be X, because some of it's going to react. So that means we've got to do a second reaction. Reaction 2. And so here's what you do. You take the product, the conjugate base, and since it's a weak acid, you run it through an ice table. Okay? And its initial concentration is X. We just figured that out. At the end of this reaction, X is the concentration of HC2O4 minus. So that becomes the initial here. So that would be 0.0544. Water's a liquid. These start off as 0, but actually H0 plus is not initially 0. It's X. So it's also 0.0544, right? Look what happened in that first reaction. X here and X here. So this one right here is going to be the same. This one right here is going to be the same as that one. Now, because this one is 0, Q is still 0. 0 times 0.0544 divided by 0.0544 is still 0. So that means the reaction still goes that way. We don't need to worry about H2O. So then this goes up, and this goes up. Now, at equilibrium, we'd have 0.0544 minus X, X, and 0.0544 plus X. So now, Ka2, which is, again, you have to look that up in a table, it's 6.1 times 10 to the minus 5. Would be equal to the concentration of C2O4 minus, which is called oxalate, times H3O plus, which is hydronium, divided by HC2O4 minus. That would be equal to X 0.0544 plus X divided by 0.0544 minus X. Okay, so now this is pretty interesting. What do we do here? Because the value of Ka is small, only a small percentage of it is going to ionize. So that tells us something, actually. Let me see if I can come back over here and create some more room down here. Ka2 is 6.1 times 10 to the minus 5, 0.0544 plus X times X over 0.0544 minus X. Here's what happens. If X is going to be very, very small now, compared to 0.0544, we can simplify this, just like we've done before. We'll simplify it to 0.0544 times X. So I'm just getting rid of this X here and this one here. Okay, now look what happens. Now we find that X is the only thing left. So that means X is that value right there. So now, for this second step, coming back over here, right, we got that right there. Now we can figure out what these are going to be. It's going to be the concentration of, I'm just going to bring it down a little bit, concentration of H, HC2O4 minus is 0.0544 minus X, which is 0.0544 minus 6.1 times 10 to the minus 5, right? Because X is equal to that value right there. It's actually equal to Ka2. Isn't that interesting? Now, the second one in this equation is right here. Concentration of C2O4 minus. That's a C, sorry. 2 minus. That's X. So that's 6.1 times 10 to the minus 5. Concentration of H3O plus. That's X, except it's not just X. I'm sorry, it's 0.0544. Let's come back over here. 0.0544 plus X. So that's 0.0544 plus 6.1 times 10 to the minus 5. Okay? So now we've got our final results. We can calculate everything. There's 4 substances. There's the original acid, H2C2O4, and we did that earlier. Okay? We figured out that H2C2O4 was this right here, 0.0456. Which, quite frankly, is 0.046 molar, 2 sig figs. Okay? But then we've got HC2O4 minus, which is the conjugate base of H2C2O4, and we figured out that that was 0.0544 minus 6.1 times 10 to the minus 5. Here's what happens, though. To 2 sig figs, if you do this difference, this number is so small compared to that one, it's really just this number here. So it's really 0.054. So there's that one. Then we've got the C2O4 2 minus, the conjugate base of the second acid. And that one is 6.1 times 10 to the minus 5 molar. That's just X. And then we have the hydronium. And that one was 0.0544, which we got from the first ice table, plus 6.1 times 10 to the minus 5 from the second ice table. But again, 6.1 times 10 to the minus 5 is tiny compared to 0.0544. So it's really just 0.054 molar. And there's our 4 values. So once you reach equilibrium, what you find is the original oxalic acid, a little over half of it dissociated, and then the weak acid HC2O4 minus, almost none of it dissociated, very small amount. So it didn't really affect the pH at all. It stayed at 0.054, but you do form some oxalate, C2O4 minus 2, a very small amount.